We'll now discuss more advanced Datastore topics on query, index, and transactions. These are 3 topics I'll cover on this lesson. How does Datastore work on query? We'll discuss what the reason is behind these kinds of restrictions and how they're actually an essential technology to make it very scalable. The second topic will be the workarounds based to overcome those restrictions. Then lastly, I'd like to discuss about transactions in Datastore. Because Datastore is not a traditional database, the behavior of the transaction in the Datastore is completely different. There's an important concept called entity groups, which we'll spend some time on. So, how does Datastore work on query? Bigtable doesn't support query. In ordinary traditional relational databases, you'll always be able to search on the value of a current column. But Bigtable doesn't allow you to do that. Bigtable can search only on a key. Then how does Datastore support a query? In Datastore, queries will be executed as an index scan of Bigtable. So this is the big difference between Datastore and traditional relational databases. Query is executed as an index scan. So think about a simple query like this. When it's trying to select all the person entities with conditions like height property must be less than 72. For this query, it will be executed as a range scan on Bigtable with an index table for height. Recall in the Datastore introduction session, there was a function called memscan. Bigtable can scan on the key, not on the values. So by having an index table on Bigtable like this, which has the property name and the property value in its key, then you can implement a query like this on Bigtable without reading the actual values. Actually, we're using values from the columns in the key of the index itself, so that we can search on the values by doing the index scan. This is how Datastore makes queries so scalable. Without any index table, most of the queries on Datastore are built through exception, or you have an error. But this is quite different than the traditional indexing in a traditional database. In relational databases, you might want to add an index just for the performance issue. If you don't have any performance issues, like if you are just having 100 rows in a table, then you don't have to put any index on the traditional database table. You can still run a query without having any index. But in Datastore, you cannot execute almost any query on Datastore without an index table. This is not a restriction. This is a key technology. It's why Datastore query can be practically limitless. If you are using a traditional database, there's a certain scalability limit on the query. But on Datastore, you can just run a shard among the multiple physical servers. But you don't have to care about that by yourself. All the underlying layers, like Datastore and Bigtable layers, are taking care of all that, sharding all the data into multiple physical servers, or dispatching the queries onto your multiple physical servers. That's not achievable in a relational database. The most important point is that the index scan makes query performance for the size of your results, not with the data set. So no matter how many entries you have, it doesn't affect your performance of your query. Your query performance will be affected only by the size of the result set. If you are trying to get millions of records as a result set, you will decrease your query performance. The size of the whole data set won't affect your query performance. But how does this support various queries just by index scans? As you saw, the index scan mechanism is so simple. So you might wonder how it can support complex query conditions like where or order by clauses. The answer is various kinds of index we have on Datastore. One is the SingleProperty Index. SingleProperty Index will be working for queries with a simple sorting or filtering, just like this. So here's a sample query with very simple conditions like name property equals John. If you ran a query like this, this query will be converted into an index scan on the SingleProperty Index for name property. For every single property or entity, there will be a SingleProperty Index automatically created for you. You don't have to define explicitly to build that index. Every single property index will be automatically created for all properties. So if your entity has a property called name, then the single property index will be created automatically. And if you execute a query like this, then it'll be converted and executed as a range scan on this index table, or index scan for a key, for a parent name and John. This is actually a key of the index table. So these are the keys of the index table, and there should be a value, which is the key for another table. This is how you can write the simple query on Datastore in Python. Because you are not directly handling your big table, you can just use the simple query language like this. This is another example of the queries that is executed to be a single property index, which has the unique quality of filtering, like the greater than, equals, or if-then operators, and also sorting using the order by clause on a single property. We're still handling filtering or sorting on just one property, so that those queries can be handled by the single property index. If you are handling just one property on your query, then these queries can be executed as a range scan on a single property index scan. In this case, it's trying to find a name which starts with B, so it will be converted to a range scan, from Bob to Brad, for example. And there's something else you should notice, that single property index actually uses two index tables. One is an ascending table, and another is a descending table. So every single property, there will be two index tables automatically created. So this single property index can support queries like this, like the equality filters. At this point, for this particular query, you don't have to have a composite index that'll be discussed later, because Datastore will merge the results of the queries for each properties into one automatically. So Datastore will execute a query for the first name equals Bob, and then execute a query for last name equals Jameson, then merge the result into one. Also, inequality filters or not equals attribute can be executed by the single property index like this. And not equal to filter, like last name not equal to Bob, will be converted internally as a query like this. This should be OR actually. First name Bob. This will also be handled as a single property index too. Let's discuss the more complex query. For more complex queries that would involve more than one property, you would need to create an index code or composite index. This is also known as a custom index. This is an example of the query for composite index. If you are using an inequality filter on one property and combining it with the inequality filter on another property, then you would need to build your composite index for that. And a composite index has a logical value, has values for logical properties like kind name, and values for the last name, and values for the first name, so that this Datastore can convert this kind of complex query into a simple index scan. The combination can be very complex, with lots of tables being created for that composite index. You, the developer, have to explicitly define that by your configuration file. This is an example of a query for a composite index. In Java, you can specify that in a file called Datastore Index, or in the index.yaml file. In Python, you can just use your index.yaml file. Or you can write the definitions of the composite index like this. You can specify the kind name and the rest of the properties with the property name and the directions you want to have. By specifying this and deploying this application onto the cloud, Datastore will start building the composite index for you. Composite indexes can support queries like this, as we just saw in this example, the queries with the inequality filters and equality filters on other properties, or the queries with logical sort orders. This will be a very popular use case for the composite index. So let's move on to the workaround part. How can we make Datastore query operate almost as flexibly as a relational database query? We cannot say Datastore will be super flexible just like an RDB, because a single Datastore query will have to be super scalable. We'll have to have certain restrictions. For the App Engine developer, it's very important to understand those restrictions and workarounds before you start designing your data model. Like the restrictions, inequality filters and sorting needs an index. Inequality filters like less than or greater than are only applicable to the single index single properties. You cannot have the query where you are applying inequality filters onto two properties. So this is one of the major restrictions we have. There's a very close relationship with sorting and the inequality filters, because every filtering or sorting is implemented as an index scan. So it means if you want to do any sorting, you have to prepare everything sorted beforehand as an index table.
One of the famous restrictions for any NoSQL database is that join is not supported. Whenever a mission-critical system gets so big, denormalization issues occur. If you're splitting this database into multiple instances, you cannot execute join operations anymore. So if you're querying like this, where you'd want to join two different tables like a person and address, you may want to put the country property into a person, not normalize the table, denormalizing the table. This means there's a trade-off between the performance or scalability and the redundancy or cost of managing multiple duplicated values onto the kind or many kinds. There are some tweaks you can emulate the join operation in Datastore. Like this, if you have to handle end-to-end relationships. In this example, each entity called person has friends, and they have an end-to-end relationship between person. In a traditional relational database, you'd have a join table called friends table, which represents every relationship between the single person. In Datastore, you don't have to have another join table to do that. You can just have a multi-valued property like this. Friends property may have a list of strings, list of the people names, so that they can write the query like this. If you want to find a mutual friend who is a friend for Bob and also a friend for Willie, then you can write a query like this. Select from person where friends equal Bob and friend equals to Willie, and location equals to San Francisco, for example. This query can be executed by using a SingleProperty Index. You don't have to prepare a composite index for this query because the Datastore will be merging and joining the result from the two different queries into one. This means that you can implement the end-to-end relationship within the Datastore result without any join operation. You can still do this for joining between the same entities, in this case, person. This example is joining two different result sets for the same entities, but it's still a major restriction that you cannot join the different tables. There's another restriction we have a workaround for the App Engine Datastore. In Datastore, you cannot execute any group by operations, or aggregate functions. More specifically, you cannot execute counts from table, so you cannot count the number of entities you have right now. To be scalable, you don't have time to look at all the entities and count them all. You do have a workaround having a special entity that maintains aggregates by you, like a counter entity, which holds the number of entities you've created. If you're doing this, however, you have to be careful about the entity's bottleneck. There are limitations like the one entity can only get one update per second. This is not a physical limit, but is kind of a design property you have to follow. Because of this restriction, you cannot simply have one counter entity to count many accesses from the users. There's a design element called a sharding counter, where you are sharding the counters into multiple entities and gather aggregated results later. You can alternatively use Memcache as a holder for that count value. Then use Datastore as well to back up the latest count number. It's hard to implement a counter or any aggregate function on the Datastore. If it's not required to get the aggregated value instantly, then you can do it later by using batch processing, by using a backend instance. There's also a very useful open source framework called App Engine MapReduce, which is using TaskQ to emulate the MapReduce framework. We won't discuss details about the App Engine MapReduce, but this can efficiently handle batch operations on huge amounts of entities on Datastore. Finally, if it's not urgent, then you can just rely on the statistics API of the Datastore. Datastore provides statistics data like how many entries you have or what kind. By accessing the API for that, and those numbers will be updated once per day. So it's a very large number, but still, you can use that for certain usages. Moving on to the aggregation function restrictions, you cannot use the minimum function or maximum function like you have in your relational database. You may want to have a single property and sort it ascending or descending so that you can find the first entity on the index to get the minimum value or maximum value. This technique in Datastore allows you to have an aggregated value, like a count or average, or a maximum, while the order of log n speed, by using a data structure called skip list. Skip list is very similar to a binary or B tree. Just like a tree search, you don't have to look for every single node to find a node. You can start finding it from the express lane. The trick is, you can just add the aggregate values on each express lane to get the aggregated value on the data store. Using this data structure, you can obtain the average or a maximum or minimum values of a range of entries in a very short time period. You don't have to scan all the entities in the range. For example, how many entities do you have from the node 1 to node 6? Using the level 3 express lane, you find 3, and then you add 2, so that the answer will be 5. There are 5 nodes between node 1 and node 6. An important thing to consider is the cost of indexing in Datastore. This is a real application which has an entity with only 25 megabytes. However, it consumes a total of 238 megabytes somehow. The rest of the space is taken up by the indexes because that entity has so many single property index tables for each property. It means you need to have 10 times larger index space than the entity itself. This is another big difference between the Datastore and a traditional database. If you want to cost estimate Datastore accurately, then you have to think about the cost of index in terms of space. You may also want to check your document called Understanding Write Cost, which explains the CPU cost you consume for building the index. For every single entity write or update, it will also update the single property index or custom index you have created. When you are using hundreds of index tables, that means updates can take a very long time. And now to discuss some final caveats. There are no aggregation functions like the lower or upper or any other functions. You may want to pre-process or pre-calculate the value, putting an additional property on the entities so that you can implement it. Because Datastore doesn't support search, there's a very useful new API called Search API, which supports full text search. It converts every query into the index scan or key, so it means you cannot be applying the irregular expressions full text search on the index scan. So instead of using Datastore, we may recommend you look into the Search API for full text search. When you're using the query, you may not see that result instantly, returning the old data instead. To avoid this, you should use Ancestor Query. Ancestor Query guarantees strong consistency. It means you're always getting the latest result of your updates. And lastly, there's a combinational explosion phenomenon that can happen on large value properties. If you're having a multiple large value properties on the query or index, because multiple large value properties on the index, there will be a 10 times 10 log of combinations of the index. So you need to be careful when you're using the multiple large valued properties on your query or index. Let's now describe how transactions can work in Datastore. Now you understand how Datastore can be scalable with its unique practice like Datascan. It's time now to understand the transactional aspects in Datastore. In Datastore, you design your data model based on consistency requirements. This is one point which is not required in traditional RDBs. In traditional relational database models, you don't have to care about the transactional requirement when you're designing your schema. But in Datastore, the data model is closely related to the transactional requirement. So by designing carefully, your data model can make your application super scalable and yet consistent. So what is a transaction? This is a recap of the general concepts of transactions. If you have any experience on the traditional database, then you already know the concept of the ACID characteristics, but I'd like to recap. In short, it stands for the atomicity, consistency, and isolation, and durability required for every transaction. A transaction is a series of operations on your record or entity. If you have a user entity and want to execute a series of operations like updating the name of a user or the age property of a user, those series of operations can be a transaction. Originally, transactions were invented for a mainframe environment, so were robust and consistent. Whenever you have a hardware failure or application bug or getting so many requests from the users, no matter how things can happen, they want to make everything consistent and reliable for business purposes. To do that, the transaction should support the atomicity, like whenever you have a hardware failure or a software failure or a transaction during the transaction execution, the result should be all or nothing. There should be no partially applied or inconsistent result. Ensure that any transaction will bring the data store from one valid state or another. As I mentioned, every transaction should be applied in a way that there is no partially applied state. Isolation means more like it's talking about the situation where you're getting so many requests from so many users at the same time, like updating one bank account from multiple ATMs, can break isolation or consistency. So your data store database has to prevent that by isolating each transaction. Durability means you have to use a hard disk drive to store the result of the data store updates. If you're storing everything in memory, you will not have any durability. So transaction means your application is robust and consistent. For simpler applications which don't require robustness, then you don't have to take care of transactions. A hobby application, for example, you don't have to use the transaction entity group I'll be discussing. Entity group is the most important concept when learning data store transactions. Because of the name, you may think that it's related to the 1-to-n relationship between tables in a traditional database. Actually, it's not. It's just a scope of transaction. It doesn't need any entity relationship we have in the traditional database. It's a scope of transactions. Each entity has its own entity group by default. It's just like if you are a person, then you are a family, we all are. Your family originally consists of just one, just yourself, but you can grow your family. Each entity has a single entity group, so there are 5 different entity groups here. Having a parent and child relationship between them, it can create one entity group. So this grandpa has so many children, a successor like dad and grandpa. This can work out as a scope of a transaction, and transaction's integrity or consistency can be secured with this group, not among the different entity groups. A potentially confusing part is the key of an entity is a very important part to clear this entity group relationship. If you're adding more and more children or successors to an entity, the successor would have an ancestor path. This is a totally new thing that was not used in traditional database. Every single key has an ID to identify each entity, but also has their ancestor, which describes who is the ancestor, dad or grandpa or of yourself. 2 formal entity group relationships. This is somewhat difficult to understand. And this is all for transactions. This is not a relationship between the tables in a traditional database. To create this kind of entity group relationship, you may want to create this kind of code. When you're creating a new entity, you may want to specify the kind of name and ID of yourself and of the entity, and the parent's key, so that it would create the total whole key like this, the key with the ancestor path. To use the transaction, you can write like this. This is very similar code to the traditional way of handling a transaction with an RDB. To tell the data store to begin, and after writing everything, then you would want to commit that transaction. If an unexpected error or exception occurs, then you would want to roll back everything. This means canceling all the updates done during the transaction so that you'll get the atomicity of the transaction. This is the same as the ordinary way of controlling transactions, but the difference is that the transaction will be rolled back based on the entity group relationship. If you're updating 1,000 rows during a transaction, then the rollback will be canceling all the updates for the 1,000 rows. But in the case of a data store, the rollback will be applied only to the entity group. That's the difference. I'd like to mention an important new feature introduced recently called Crossgroup Transaction. You can have up to 5 entity groups in a transaction. However, remember that all queries will use eventual, not strong consistency. If you design an entity group, you should make sure that every single entity group will not receive over 1 update transaction per second. In practice, it can handle closer to 5 per second, but this could be a bottleneck for your application. Because the data store needs to control the transaction across each entity group, this means sometimes we have to maintain consistency between data centers. It can be a global transaction. These are some of the key takeaways: how a data store works in a query, restrictions of queries and workarounds, and how the entity group is a scope of transactions in data store. Finally, here are some useful resources to learn more about advanced data store concepts discussed during this lesson.